Good morning, students. In today's is going to be 24th session, and the topic which we are going to deal in today's class is going to be crystal field theory. In this class, we are going to study the crystal field stabilization for weak and strong fields. In today's class, we are going to deal with the crystal field stabilization for weak and strong fields. The splitting of the 5 degenerate d orbitals of the metal ion into two sets of orbitals having different energies is called crystal field splitting. So, the splitting of the 5 degenerate d orbitals into sets of orbitals having different energies will be called as crystal field splitting. Strong ligand field splitting. If the 10 dq value is larger, it is called a strong field splitting and the complex is called as a strong field complex. If the splitting is going to be larger, if 10 dq value is larger, it is called a strong field splitting and the complex formed is called as strong field complex. If 10 dq value is smaller, if the 10 dq value is smaller, it is called a weak field splitting and the complex formed is called as a weak field complex. Coming to the weak, let us know before going ahead what is a weak ligand and what is a strong ligand. A ligand which causes a small degree of split is called as a weak ligand. If a ligand is going to cause a small degree of split, it will be called a weak ligand. But if a ligand is going to cause a large splitting, then it will be called a strong ligand. Coming to what is a low spin complex and what is a high spin complex. The complex which is formed by a strong ligand, that is strong field ligand, will have minimum number of unpaired electrons. In case of a strong ligand or a strong field complex, what happens is they have minimum number of unpaired electrons. So, these complexes are called as low spin complex, because in this case there is going to be a strong ligand. There is going to be a strong ligand and this strong ligand can pair up the electrons in the d orbitals, making available minimum number of unpaired electrons. So, it is going to be a low spin. While in case of high spin is going to be due to a weak ligand field. When there is going to be a weak ligand, what happens is this weak ligand, when it is going to approach the complex, it cannot pair up the electrons in the orbitals. So, there will be more number of unpaired electrons. So, these complexes are high spin complex. In the metal ion, when it is going to be present at the center of the octahedron, the ligands are at the 6 corners of the octahedron. When the metal ion is present at the center of the octahedron, the ligands are going to be at the 6 corners of the octahedron. The Eg orbitals, that is dx square minus y square and dz square, are directed along the axis. Dx square minus y square and dz square are directed along the axis, while T2g, dxy, dyz and dxz are going to point between the axis. So, these are the orbitals where the orbitals are pointed between the axis. Now, when there is a direct interaction between the metal Eg orbitals and the ligand orbitals, when there is going to be a direct interaction of the metal, that is the Eg orbitals and the ligand orbitals, and if there is going to be no interaction with T2g orbital and the ligand, this results in the energy of the Eg orbital will be more than the T2g orbital. If there are going to be interactions, when there are going to be interaction, it means the energy of the system here is going to increase. And if there is going to be less interaction or almost no interaction, they are going to have lower energy. So, what happens? T2g orbital will have lower energy, while the Eg orbital which are going to interact will have a higher energy. The difference between the T2g and the Eg is given as delta O or 10 dq. the Eg orbital has 3 by 5 of delta octahedral or 6 dq energy and is going to be present above the average line. Similarly, the T2g orbital has minus 2 by 5 delta O or minus 4 dq and is present below the average line. Now, if we are going to see the crystal field stabilization energy for D1, D2, D3, D8, D9 and D10. Here D1, D2, D3, D8, D9, D10 will be the same for the strong field and weak field complex. Here the stabilization energy for D1, D2, D3, D8, D9 and D10 will have the same strong field and for weak field complex, while the stabilization energy for D4, D5, D6, D7 system in strong and weak field octahedral complexes are going to be different. So if we see, this is going to be a regular octahedron, and when the ligands are going to approach, they are going to split up into dxy, dyz, dyz with a lower energy and dz square and dy square, dx square minus y square with a higher energy. Here, because they are going to, because they are going to interact with the ligands, their energy is going to be high, whereas here it is going to be lower. They are going to be stabilized by the electrostatic interactions. Now, depending upon the spectrochemical series, which is going to be a list of ligands which are going to be arranged in the increasing difference of for a given metal center. So, these ligands are going to be weaker, whereas these ligands are going to be stronger. So, as these ligands are going to approach the central metal atom, we are going to approach whether there is going to be a larger splitting or there is going to be a weaker splitting. If it is going to be a strong ligand, there is going to be a larger splitting, and if it is going to be a weaker one, it is going to be a weak splitting. So now let us just go on to consider the splitting. The splitting in case of strong field, the difference is more, whereas in weak field it is going to be small. And these are the examples in octahedral complex. So what do we observe here is in D1, the crystal field splitting, I have got what? Only one electron. So it is going to be 0.4 delta O. And since I am having 2 electrons here, it will be 2 into 0.4, that is 0.8 delta naught. So in case of 3, I am having both in strong and weak field, it is going to be 1.2 because it is going to be 3 into 0.4. Coming to D4, D5, D6, D7. In this case, there is going to be another electron, and there are two possibilities. Where the electron is going to enter. Whether the electron, in case of strong field, what happens is the electron is going to get paired up. But in case of a weak field, the electron will not get paired up. So one of the electron will enter into the Eg. But in a strong field, the electron will enter into T2g. So for a D4 system, for a high spin complex, I will be having 3 electrons in the lower energy level, that is 3 into 0.4. It is going to be 3 into 0.4, and I have got only 1 electron in the Eg orbital, so it is 1 into 0.6. So if I just go on to consider, it is going to be 0.6 delta naught. Whereas for a low spin one, this is going to be a low spin. In this case, there is going to be a strong ligand, and so the electrons are forced to pair up. Here I am going to have, in case of low spin, I will be having all the electrons are present in the T2g only. So 4 into 0.4, and this is going to be 1.6 delta naught. So this is going to be the crystal field stabilization energy. Likewise, the same way I am going to calculate for D5, D6 and D7. In case of D5, this is going to be in case of a strong field, it will have a lower spin. It is going to have a lower spin. Since I am having 5 electrons, 5 into 0.4 comes to be 2. So this is going to be 2 delta naught. Likewise, in case of a high spin one, I'll be having 3 electrons in the T2G, 3 into 0.4, and I'm having 2 into 0.6. So it get cancelled, and in this case it is going to be 0. So this is how I'm going to calculate for D6 and D7. Here there are going to be no unpaired electrons. I'm having 0 unpaired electrons, but to calculate the energy, the splitting energy, in order to calculate the splitting energy, I am going to have 6 electrons. I am going to have 6 electrons in the T2G. So it is going to be 6 into 0.4. It comes to be 2.4. But in this case, I am having 4. 2, 3, 4. It is going to be 4 into 0.4 minus 2 into 0.6. When I am going to subtract, I am going to get 0.4. So this is how I am going to calculate even for D7 1. So likewise, when we are going to calculate for D8, D9 and D10. For D8, D9 and D10, it is going to be for D8, in case of strong or weak field, it will remain as 1.2 delta naught. In case of D9 also, whether it is going to be strong or weak, it is going to be 0.6. And in case of D10, whether it is going to be strong or weak, it gets cancelled and it is going to be delta naught. So in all electronic configuration involving 2 electrons in the same orbital, the actual crystal field stabilization is reduced by the energy spent on pairing of the electrons. So metal ions with 4 to 7 electrons in the d orbital can exist as high spin or low spin complex. So metal ions only from 4 to 7 in the d orbitals can exist as high spin or low spin. Weaker ligands tend to give high spin complexes, whereas stronger ligands is going to give me low spin complex. Okay students, thank you.